Okay, and our next speaker is Arvind Gupta, who's going to tell us about following the flow's coordinated observations of stellar supergranulation with EPRV facilities across the globe. So, Arvind?
Thanks, Adam. Can you guys hear me? Cool. I'm upset that Fede didn't leave the bison here for me. So yeah, my name is Arvind Gupta. I'm a postdoctoral fellow at Noir Lab over in Tucson, but I'm going to be talking today on behalf of the EPRV Research Coordination Network Standard Stars Working Group. Lots of words, but we'll explain what that is as we go through here. To get started, can I ask you all to raise your hands if you are looking forward to the Earth Analog Survey that will be conducted by the Habitable Worlds Observatory? Okay, so like 90% of people raise their hands, and the other 10% are in the wrong room, I think. So yeah, when HWO launches, whenever that ends up being, it will conduct a survey of a sample of nearby sun-like stars to look for Earth-like planets and study their atmospheres to look for potential biosignatures. And unsurprisingly, most people here in this Know Thy Star, Know Thy Planet conference are looking forward to what that's going to do. As David excellently explained in his talk at the start of this session, host star characterization is essential for this effort, and we really need to know the stars inside and out in order to be successful there. But something that's occasionally overlooked or lost in all of that is that we also need to know the planets themselves really well, either before or after they've been identified by HWO. And over here, my mouse is over there. Okay, sorry guys. For Earth-sized planets, mass measurements are going to be a major challenge. In this figure here, this is from Caleb Harada's recent paper. Caleb's in the audience over there. Hi. This is showing our current detection sensitivity limits to Earth-like planets with radial velocity data from HARPS and high-res. And the purple contours there are the 50% completeness for individual stars, and the black is the median of the sample. And this is for all of the potential HWO target stars from the XEP sample. And we can see that that green line down there, that's the mass of an Earth. So we are nowhere near getting there. Now, the good news is that while Caleb was using the latest and greatest data, high-res and HARPS are no longer the state of the art. Over the past decade or so, the community has put in a ton of effort, and thanks to a lot of great technological developments, we have commissioned and launched this suite of a new generation of extreme precision radial velocity spectrographs. I'm showing their wavelength coverage on the horizontal axis here, and the aperture of the, oh, this is hard to point, sorry, the aperture of the telescope on the vertical axis. And what I want to highlight is that in the optical, all the spectrographs on the left, yes, your left side of this plot, in the optical, we're getting to close to 50 centimeter per second precision and stability. So getting closer to that centimeter per second level we need for Earth analogs. And in the infrared, we're getting to about a meter per second. So most of the data from these instruments is still proprietary, but we do know that many of the teams here are surveying and trying to follow up a lot of these HWO target stars to collect the RV baselines we'll need for the Earth-like planet mass characterization in the future. And they are getting us, they're breaking through those previous sensitivity barriers established by high-res HARPS, the previous generation of spectrographs. Of course, every time we overcome one challenge, we run face first into another. And as we've talked about in some previous sessions here, as well as in Fede's talk just now, stellar variability is a significant obstacle to Earth-like planet detection. This figure here is from the recent EPRV working group report a few years ago. What it's showing, and the bottom there, is that the gray points this is a section of the HARPS North solar data time series in gray, and the green line there is the signal from an Earth analog. It's a line, it's relatively flat because compared to how variable stars are, the planet signal is almost undetectable, or in this case, it is undetectable. And this has arguably been the #1 focus within the field for the past 5 to 10 years, or at least as long as I've been in this field. Which means that people have done a lot of amazing work, come up with very clever and creative analysis techniques, including like the one Fede I just talked about, to model and mitigate that stellar contribution to the radial velocity signal. And these have been very effective, bringing the residual contribution after that mitigation down to the sub-meter per second level for both the sun and for actual stars. But we're really getting into the weeds here. Down at the sub-meter per second residual level, there's still signal there from the star. And even with our extremely precise spectrographs, there's signal there from the instruments. So this is where even our best mitigation techniques may begin to fall short. Because ideally, when we're modeling our signal, we want to perfectly disentangle the stellar and instrumental contributions. We want to know which is which that's contributing to that there. But it would be a stretch to say that either of these are sufficiently well characterized for any spectrograph or for any star that we can really realistically accomplish something like this. Because there's always going to be a variety of ways to decompose the observed signal, and they could appear to be equally good if we're working with limited information. So if we can't identify the correct breakdown here, we're going to draw the wrong conclusions about the stellar astrophysics and about the instrumental systematics, and that should raise some major red flags about our ability to accurately characterize either of those things. One way to solve this would be to observe the same star simultaneously with a handful of different instruments, where we would see different signals with all three. We might do some sort of PCA decomposition or some other analysis where we can break down that signal and identify common features, that would be the star, what everything is looking at, and then distinct features would be the instruments themselves. This is way overly simplified, but there's way more nuance than I have time to talk about here, so this is just to illustrate the idea of the method. I'm going to switch gears, we'll come back to that, but right now, for those of you who attended Neva Sullivan's talk yesterday, you should know everything about supergranulation. It's one of the sources of RV variability that is still really frustrating us. It's been very, very difficult to deal with. And what I'm talking about here is this component of this is a solar power spectrum. It's this component of highlighted in red that's fairly broad and covering this low frequency range. And in the sun, it contributes about 0.5 meter to 1 meter per second of variability. So as I said, supergranulation has been notoriously difficult to characterize, particularly in stars, because this is what I'm showing here is a simulation based on some of Neve's recent work, actually. And even if we could afford to sit on the same star and observe it all night, night after night after night after night, the signal from supergranulation varies just slowly enough that we'd still miss a lot of critical information in the gaps between those nights whenever the sun is up. Without a spectrograph in space or one at the poles, we're going to be limited by Earth's rotation, and we won't be able to properly characterize supergranulation in stars. To tie this back to the case I was making earlier at the start of my talk, we can again look to a solution that uses multiple spectrographs. So the facilities that are pictured here, they span almost 180 degrees of longitude, from Spain and the Canary Islands on the east out to KPF Maroon X in Hawaii out the west. And we can take advantage of that to effectively extend the length of a single night of observations by continuing to follow a star even after the sun has risen in one location. So this is the same, in gray is that same simulated time series I showed earlier, but now these are points from 8 different spectrographs. These are also simulations, not data yet, showing that we can minimize those daytime gaps and also significantly decrease the cost to an individual spectrograph by using data from multiple. So we're not sitting on it all night with a single one. We can stagger them a little bit to cover that baseline. Now, a data set like this would be fantastic both for studying supergranulation and for characterizing instrument systematics by cross-calibrating them together. But coordinating something like this is way easier said than done. I'm sure people here have submitted observing proposals before, and submitting 8 of them to 8 different agencies with different time allocation committees and policies and different semester deadlines and all that is challenging. But we still thought it was going to be fun to do. So as part of Jen Burt's EPRV Research Coordination Network, she's leading a standard stars working group, and a lot of us in that group decided that we wanted to try to do this. So we got together last spring, submitted proposals to NUID, Maroon X, Espresso, KPF, APF, which is Precision RV, not EPRV, but we thought it would still be interesting to check that one. And we had commitments from Express and HARPS North to contribute their time as well if these other proposals were successful. And then we also got Carmen's director's discretionary time in the end as well. So we submitted these, and they were surprisingly well received. We got proposals through to NUID, MaroonX, KPF, and APF. We didn't get espresso, but it's the VLT. It's really oversubscribed. I mean, what were we thinking was going to happen? So we got those through. We got some data. The weather didn't quite work out for Harps North and Carmen's. So the green points here are Harps North. They were, I think there was really high humidity, not great weather, so this is certainly not indicative of the instrument's actual performance. Carmen's was similarly dealing with some humidity issues. But if we take those out, we're looking at a different star here. This is Tau Ceti, which we heard about yesterday too from Rachel. The MaroonX has two different channels, the blue and the red. And the red channel, after speaking with their team, it turns out they were actually dealing with some calibration issues which are yet to be resolved. So that's one more instrument down. But we had 3 instruments that got data for 4 stars over this 5-night span, as well as Express for another star for a few points in there too. And we actually somehow managed to pull off this coordinated data set to observe these stars simultaneously with multiple instruments. So we're really still just starting to explore this. We got these observations were taken in September. We didn't get most of the data until late last year. So we're digging into this now. The first thing I want to highlight is the vertical scale here. This is -2 to +2 meters per second for each of these stars. So if you look at the scatter, I mean, for HD 4628 down there in the bottom left, that's a peak to peak of less than 2 meters per second with 4 instruments together, or 3 instruments together looking at that. So the first takeaway is that the scatter really is low even when we're considering all the instruments together. The other thing I want to highlight is for Tau Ceti there, we can kind of see that the instruments are also sort of following the same trend over the course of each night. So these are stellar signals that we're seeing for Tau Ceti with all of the instruments together. There's still quite a bit of work to be done with this data set. MaroonX uses a template matching method for the RVs. KPF and NUID are cross-correlation function methods. So I'm working on currently running a template matching method on the NUID data so we can do a more one-to-one comparison of the two. But there's work to be done. We're going to get together and do this and try to figure it out. The big downside from this data set was that we lost the European instruments, the ones over across the Atlantic. So we didn't get that extended baseline that we need for supergranulation. But we are trying this again. So we got more successful proposals for this coming June. And we're going to try to look at a different parameter space of stars to try to accomplish that. So the June stars are going to be more sun-like. These were late G, early K. Yeah, so the next steps here, we're going to do some reprocessing of the data, try to get some improved calibrations with, and apply mitigation techniques to see what we can get out of the data set. We'll have those new June data later this year. And then at the EPRV6 conference, if anybody's attending that, Neve will be leading a splinter session to look at supergranulation and also specifically at this data set to try to hack on it and see what we can pull out, because this is not something that can be done by one person or one team, because we need to really know the intricacies of each of the instruments that contributes to the data. I will leave that up, and I think my time is up. So. Okay.
Jamie Tyre, University of Florida. Do you have simultaneous photometric monitoring, and can you use the granulation signal in that to help you?
So we do not have simultaneous photometric monitoring, or at least as far as I'm aware. These are all relatively bright stars, so they may be saturated in TESS, but we haven't looked at whether TESS was observing. So we should do that, yeah.
Just a comment on that last point. So TESS would be perfect for this. So I would actually encourage you to think about targets that TESS is currently observing, ideally with 20-second cadence, which works really well for these very bright stars as an additional piece of information. The question I had is the cadence. Maybe you mentioned this and I missed it, but what are the cadences of the individual instruments that you're getting? And are you thinking, or are you considering having a fast enough cadence that you can actually sample the P modes? Because that would be interesting to do a comparison between the different instruments for a scientific astroseismic reason, rather than correcting for it.
That is a great question. For the data we got in September, we binned the P modes for the instruments on the smaller telescopes. For KPF and Maroon X, we sampled the P modes for at least a couple of the stars. Just with the extra glass, we could afford to do it. For June, we will certainly consider that since those observations have not happened yet. We're still in the planning stage. Yeah.
And with that, I think we're out of time for questions, so let's thank Arvind again.